If you are going to use or produce your own inductors, I give you a equation that relating to the geometry of the inductor. Now the equation can be computed. The inductance can be computed by using this formula: L equal to N square mu A over L, where N equal to the number of turns in the coil. Mu, it is the permeability. In Chinese, it is so-called 導磁率. Okay. Okay, and it is a material specific parameters. Different material will have different permeability. Okay, A is the cross-sectional area of the inductor, and L is the length. Now, normally your inductor will be wound on a core. This core normally is a ferro material. That means they may contain iron inside in order to improve the inductance. Okay. Actually, the inductance you may consider that it looks like a solenoid 電磁石 OK 電磁石都係呢個結構嘅 OK when you pass current to the coil due to it become a magnet. Okay, it become a magnet so that it will attract some iron, okay, or ferro material. Okay. Now we call that the IV characteristics of the inductor given by V equal to L di dt. Again, if you rearrange the equation V dt equal to L di and take integral at both sides, you can get this formula: I equal to 1 over L integral V d tau plus IT naught. IT naught actually it is the initial current of the inductor. Now actually this is the integral form of the IV characteristic, but similar to the capacitor, I may say the derivative form is more important because most likely we're using the derivative form in our analysis, okay, rather than the integral form. Now for the power calculation, P equal to V times I, and V can be replacing by L di dt, so you can get this formula: P equal to I L di dt. And if you take integral of the power function, you can get the energy. And after you solve the integral, it gives you W equal to 1 over 2 Li squared. Okay? Now we give you some example. Now the first example, we say that find the current through a 5 Henry inductor if the voltage function is given by Vt equal to 30t squared for t larger than 0, and Vt equal to 0 for t smaller 0, and also found the energy when t equal to 5 seconds, and as we assume that the current larger than 0. Okay. Now, well, we know that the IV characteristic of the inductor is given by I equal to integral 1 over L integral Vt dt plus IT naught. And now L equal to 5 Henry. You substitute the power function, voltage function by 30t squared, and integral from 0 to t. Okay, because when t is more than 0, it is a 0. And IT0, you consider that the current initially passing through the inductor is 0. So IT0 equal to 0. So after you solve the integral, 30t squared will give you t clip over 3 times 6. Okay, and after you dividing by 5, you get this formula. Or at the end, it is equal to 2 times t cubed. Okay? And now this is the current function. If you are going to find the energy, you are going to find the power function. And power function is given by V times I, and it gives you 60 times I, 60 times t to the power 5. Okay, and now you can compute the energy by taking the integral from 0 to 5, 60 t to the power 5 dt. And after you solve the integral, it is equal to 60 times t to the power 6 over 6. From the lower limit is 0, the upper limit is 5. And at the end, it gives you the energy equal to 156.25 kilojoules. Now this is one of the methods you can find the energy. On the other hand, you can directly apply the formula 1 over 2 Li squared. You substitute the lower limit and upper limit to the formula. At the end, you get the same answer. Okay? You can either using any approach to solve this example. Okay. Again, this one I think not relating to circuit theory. Instead, it relating to mathematics or calculus. Right? Now we show you another example. Now in this example, we say that the circuit is under the DC condition. And we are going to find I, the current passing through the current flow out of the 12 volt voltage source. We see the potential difference across the capacitor and IL, the current passing through the inductor. Okay. Now remember that under the DC condition, the capacitor looks like an open circuit. How about the inductor? Now for the inductor, we say that the current and voltage is not changed. Therefore, the inductor looks like a short circuit. Okay? Now therefore, we give you before, the DC condition means that the components are at the steady state, so that the current is not changed, the voltage is not changed. Therefore, if the current is not changed, okay, now remember the IV characteristic, V equal to L di dt. Okay, if current is not changed, it is equal to 0, and V equal to 0 also. So that if you remember, if a component with potential difference equal to 0, it means that R equal to 0. So it is a short circuit. Okay? Therefore, every time when we talk about it is a DC condition, your inductor will be replaced by a short circuit. Okay? Now in this circuit, again, this part, the capacitor, is an open circuit. Do you have any current passing through the 4 ohm resistor? No, it is equal to 0. So, low potential difference. V equal to 0. So, this VC means that it is the potential difference at this loop to this loop. Or it is equal to the potential difference of 5 ohm, because at this path you have only a 5 ohm resistance here. Okay? And now you have a single loop circuit only. The 4 ohm resistance has no effect, you can delete it. Okay? In this circuit, this R equal to IL, because you have the series connection here. Therefore, I equal to IL equal to 12 over 1 plus 5, or equal to 2M. Okay? Using the Ohm's law, you can get I and IL equal to 2M. And now, the current passing through the 5 ohm resistance equal to 2M. So VC equal to 5 times I, and it is equal to 10 volt. Okay? And now you can compute the energy by using 1 over CV square for the capacitor. You get it is 50 joules. For the inductor, you're using 1 over 2L IL square, and it gives you 4 joules. Okay? Now, any question here? Okay, you can summarize the DC condition that when you have a capacitor, you replace it by an open circuit. When you have an inductor, you replace it by an open circuit, and then make the calculation, just like for in your DC circuit. Okay? Now we continue. Now we give you more about the properties about the inductor. Now we have already told you when the current through the inductor is a constant, the voltage across is 0 because V equal to L dI dt. When dI dt equal to 0, your V equal to 0. Therefore, it looks like a DC short circuit. Now, just like the capacitor voltage, that it cannot make a sudden jump. For the inductor current, we cannot have a sudden jump also. Okay? If I say at the beginning we have 0 amp, and now we jump a current of an inductor to 2 amp. Can this happen? Now we say this cannot be happened. Okay? Now this is because, again, when you consider the IV characteristic of the inductor, di over dt means the slope. Okay? So if you have a sudden jump, it means di over dt will become an infinity. Or you may say, again, you have a infinite power supplying to the inductor, that it cannot be happened. Okay? This cannot be happened. So, just like the capacitor voltage, you can allow a gradual change. Okay? A gradual change about the inductor current. Okay? So, the charging curve may like this one, or the discharging curve may like this one. You cannot have a sudden jump. Okay? Or you may experience that when you switch on the power supply, sometimes it may appear a sparkling, right? 有啲閃電啊，放閃啦，係嘛？就唔係講人啦，講個電仔啊嚇。咁嗰啲電喺邊度嚟嘅咧？就係啲 sudden jump, it will produce a high voltage. Okay, a sudden sparkling, and it will create a large voltage. Okay. Now here we talk more about the inductor that, like the ideal capacitor, the ideal inductor does not dissipate energy, but it stores energy inside. It will not change the energy into heat, light, or another form. The energy stored inside will be returned to the circuit later during use. But for the real inductor, it will have some internal resistance. Therefore, the model of the inductor may like this. The inductor may connecting in series with a internal resistance, in. Okay. Therefore, you have the winding resistance in series connection. And also, now, if you look at the coil, now the distance between the coil path is very close, so that it will create a capacitor effect. Therefore, the actual model you may add a capacitor in parallel to the inductor, but both the internal resistance and this capacitor are very small, so you may not take care of them into your calculation. Okay. But if sometimes if you find your calculation is not accurate, you may need to consider the internal resistance and also the trim capacitance, okay, in your calculation. Okay, but normally, no need to take care about these two calculations. Okay. Now we are going to give you some equation on reducing the inductor network. Now firstly, we have the series inductor. Now consider this network that we have n inductor connecting in series. We assign a voltage for each inductor, and they have the same current, and we have the voltage source. Okay. Now we apply the KVL. Okay. This gives you V equal to V1 plus V2 plus ... up to Vn, where we give you the formula here. Okay. And now, what is the IV characteristic of the inductor? You have V equal to L di over dt. So each of the voltage can be replaced in terms of the inductance and the current. This becomes L1 di dt plus L2 di dt plus ... Ln di over dt. And you found we have the common factor di over dt. You take it out, it becomes di over dt times L1 plus ... up to Ln. And now, for the sum of the inductance, you can replace it with a equivalent inductance, and it becomes Leq di over dt. Now, in other words, you can reduce a series inductor network into a single inductance. Okay, because now this formula actually is the same to the IV characteristic of the inductor. So we give you the formula just like to what you did in the resistor network. When you have series inductor, you add them together, and then it can become a single inductance. Okay. Now on next page, we give you the formula. At the end, you find that if you add all the inductance, you have the resultant inductance. Okay. Now how about the parallel inductor network? Now we consider this circuit. For each inductor, they are connecting in parallel, where they have the same voltage, and each inductor we assign a current. Okay. Now we apply KCL at the top node. You have I1 plus I2 plus I3 plus ... up to In equal to I. Now, but our IV characteristic of the inductor given by V equal to L di dt. So you cannot apply this formula because you don't have di over dt. So what will you do? You do the same thing as just like the capacitor. You take derivative at both sides of the KCL equation, so that this gives you I1 dot plus I2 dot plus I3 dot plus dot 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 up to In dot equal to I dot. Now, actually, you don't do any differentiation here. You just replace the symbol or add a dot at the top of the current. Okay? But now you can replace the IV characteristic so that I1 dot will become V over L1 plus V over L2 plus dot 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 up to V over Ln equal to I dot. And you have the common factor V, so you take it out. V equal to 1 over L1 plus 1 over L2 plus 1 over Ln equal to I dot. So this time you can reduce the parallel network, okay, using a single inductance. That you're using the sum of the reciprocal of the inductance equal to the reciprocal of the inductance, LEQ. At the end, it becomes V over LEQ equal to I dot, where this is the IV characteristic of the inductance, so that the parallel network can be reduced into a single inductor. Okay? Now, if you look at the equation very carefully, you find that you are using the parallel resistor network calculation in here. So it is nothing new to you. You do the same thing when the inductor is connecting. The inductors are connecting in parallel. You're using the resistor network calculation, then you can reduce the parallel resistor network into a single inductor. Okay? And again, the formula using the integral form, but I have proved that you can using the derivative form, you can have the same conclusion. And at the end, you have this formula. Okay, and we say that the parallel combination resembles that of the resistance. You're using the same technique to reduce the parallel network, the parallel inductor network. Okay? Now, and now we give you an example. Now you find that we have the inductor network like this one, and you are going to identify which part is in series connection and which part is in parallel connection. Okay, again, if you don't know, you can assign the label. Now this is loop A, loop B, loop C, loop D, loop E, loop F. Okay, and you can find that loop D, you have two components connecting. Therefore, it is series connection. Also for loop E, okay, because you have two components connecting to loop E. So this bunch are 3 inductor connecting in series. You put down 20 plus 12 plus 10. Okay? And when you reduce this path into a single inductor, you find that the inductor connecting to CF. And CF also containing another inductor, 7 Henry. So this path, this inductor should be parallel connection. Okay? And the other two, actually, they are in series connection. Therefore, you add 4 and add 8, you have the equivalent inductance by using this formula. Okay? So So at the end, you get the answer. This is equal to 18 Henry. Okay? I think that this example is not that difficult because it is more or less the same to your resistor network, right? If you know how to solve the resistor network, the inductor network or the capacitor network is not a problem to you, right? Now here we give you a summary about the capacitor and inductor network. Now you can find in this table we give you the equation for capacitor and the equation for inductor. And also we make the comparison with the resistor also. Now you may find that, oh, will I ask you to remember all the equations? The answer is no. Now basically I highlight the equation to you that you should know the IV characteristic of the capacitor and inductor. That's enough. Because most of our formula make use of these two formula to generate our solution. Okay, therefore you should know these two equations only. The others, actually, they can be derived, okay, by using these two formula. Okay, therefore, you may consider that they are the Ohm's law of capacitor and inductor. Therefore, they are very important. Okay. Any question up to now? Now for the application of the inductor and capacitor, now we give you some points here. Now actually, nowadays most of our electronic devices, now we seldom have inductor because they are bulky in size. They are very large. Therefore, we make use of the capacitor to replace, okay, the inductor. The technique is that we using the operational amplifier together with capacitor and resistors. Then we can generate an inductor. Okay, but this device, it is outside of our syllabus. Therefore, we don't talk too much about this technique. Okay. Now for the capacitor or inductor, both of them, they can generate a large amount of current and voltage for in a short period of time. Therefore, they are very useful to start up any application, just like the motor. Okay? And also that they can be effectively used as a filter in order to remove the noise or any sparkling effect in your signal, okay? Because they can be made use of filter. Okay. Now for the capacitor, we have a special application using in the radio or television, using the technique so-called frequency discrimination. Actually, this technique, it is going to identify which frequency is inside in your signal, and they are made use in the tuner. Okay, you tune the radio station or television station using the capacitor. Okay， 而家就唔用呢個方法嘅，而家所有嘢都數碼化嘅嚇。以前咧就你拆開個收音機咧，你就見到有啲有個 variable capacitor 嘅，咁你扭嗰粒掣咧，你就會tune到個台啦，係嘛？OK 就做緊呢樣嘢啦，frequency discrimination 。OK。And now we move to our part about the first order circuit. Now actually we told you that at the beginning of the lesson we said actually the first order circuit comes from first order differential equation, because when you give analysis to the circuit, its output is a first order differential equation. Therefore, we give the name the first order circuit. Now we talk about first order circuit. You can imagine that we can have second order circuit, we can have third order circuit, but it is not inside our subject. We don't describe the second order or the higher order circuit. Okay. Now, however, unfortunately, in your engineering mathematics, you have the second order differential equation. Okay. So, at that part, if I am correct, your lecturer may using the circuit example to explain to you how we can generate the second order differential equation. Okay? And at that time, you can know how to solve the differential equation. But as I have said that, now in this part, I don't ask you to solve the differential equation. Instead, I will give you the general solution, like this one. Now, what is about the first order circuit? We mainly have two types. Either resistive capacitive RC circuit, or resistive inductive circuit RL. So that we never have RLC circuit in this part. No. Because when you have RLC, most likely you have a second order circuit. Okay? Now, actually, when you have this RC or RL circuit, now we needed to take care about the two excitation. Okay? One is so-called the initial condition. We consider before you change the circuit, you consider the capacitor voltage and inductor current. Okay? Another excitation, we consider the final condition. So that when the time approaches to infinity, you consider the capacitor voltage or the inductor current. Now, and also here, now due to the continuity about the function, we consider the voltage for capacitor and the current for inductor. Okay, now this is because if you consider the current of capacitor, you find that the function is discontinuity or discontinuous. Similarly, if we consider the current or the voltage of the inductor, you find that it is continuous. Therefore, we don't consider them directly. And actually, every time when we consider the capacitor, we may ask you to find capacitor voltage. On the other hand, if I give you an inductor, and you are going to find the current. Okay? Now, here, we give you the general solution about the capacitor voltage and inductor current. Okay? Now, actually, they have the similar form. Okay? Where VCT equal to VC infinity plus bracket VCT naught minus VC infinity times e to the power minus t naught over REC, REQ times c. Okay? Now we will explain later for each part of the general solution. Now for the inductor current, you have the similar structure. You have IL infinity plus IL T naught minus IL infinity times e to the power minus REQ times T minus T log over L. Actually, now Vc infinity or IL infinity means the final condition. And Vc T log and IL T log means the initial condition. Okay? And together with the RC parameters and RL parameters, now they are more or less the same. Okay? Now therefore in our part, if we can apply the general solution directly, it means that every time you look for the initial condition, you look for the final condition, and also the time constant that we are going to introduce to you later. Okay? By finding these three parameters, now we can solve our first order circuit by using the general solution. Okay? And immediately you may ask me, will we need to memorize the two equations? Now, unfortunately, this time they are very important. So I suggest you to memorize these two general solutions as far as you could. Now, but it is not that difficult if you see what we did later. Okay? Now just put the general solution here, or later you may find how we can apply the general solution to solve our problem. And now we firstly told you how can we solve our first order differential equation. The first problem we face is the source-free RC circuit. Now the meaning of source-free is that you do not have any sources inside your circuit. We say that the DC source is suddenly disconnected, just like this one. You cannot find any DC source inside. Okay? Now the problem is like that you may connect originally a circuit with a switch to the RC circuit. But now you open the switch, then the source will be disconnected from the RC circuit. Okay? Now, you may find that in this RC circuit, after the source has been removed, the energy stored inside the capacitor will release to the resistors, so that the voltage of the capacitor will eventually go to zero, so that you may find the Vc infinity equal to zero. Okay? It tells you because the final voltage should be zero, so Vc infinity in our general solution it is equal to zero. Now, consider this circuit. We are going to generate some equation. We can apply KCL to this load. If the current passing through the capacitor is IC, the current passing through the resistor is IR. By KCL, you can put down IC plus IR equal to 0. Okay? And in terms of voltage, you can replace each of the current in terms of voltage, just like what you did in nodal analysis. Right? Now, IC equal to C dV over dt. And IR equal to V over R. And immediately, this gives you a differential equation. Okay? You should learn in your engineering mathematics, right? It is a homogeneous differential equation. Right? 應該學到嗰度咯喎，係咪啊？未啊，未唔緊要，遲啲學嚇。有好多 terms 我呢度唔用嘅，喺個咩 homogeneous 啊、inhomogeneous 啊，我冇呢啲咁嘅嘢嘅。OK？ Now you can solve this differential equation that now you now rearrange the equation. You have dv over dt equal to minus v over rc. Okay, and then we rearrange the terms. I put down in here. You have dv over v equal to minus 1 over rc dt. Or you can take the integral at both sides. Then, after you take the integral, you get the answer. Okay? You can find on next page, we give you the answer. Now, we said that initially the capacitor voltage is V0. We apply KCL and we come up with the first order differential equation that we told you before. Now, after we solve our integral, okay, now we can get this formula. Okay, where lateral log V equal to minus T over RC plus lateral A. Lateral A, you may consider that it is a time a constant, an arbitrary constant. Okay. Now, if you take exponential function at both sides, okay, and you can get this formula. Okay, Vt equal to A exponential minus T over RC. And you can now substitute Vt log equal to V log into the formula. Okay. Actually we put 0, T log equal to 0. And this gives you A e to the power minus 0 over RC, which is give you A. That means your integration constant A equal to V log. So this gives you the solution to our source-free RC circuit, where Vt equal to V log e to the power minus T over RC. Now when you compare with our general solution, now our general solution gives you that Vt equal to V infinity plus Vt log minus V infinity times E minus T over RC. Now you find that now your V infinity equal to 0. Okay? And Vt log equal to V log. So immediately it gives you this formula. Right? So I told you before that the general solution is very important because you can substitute the initial condition, final condition, and the time constant into the general solution. You can get any all kind of the solution in the first order circuit. Okay. Now, any question here? Now we give you some analysis to this equation. Now this is what we call the lateral response, because it comes from the response without any external source. Okay, the lateral response. Okay, and actually when you plot this response, you find we have the exponentially decay from the initial voltage. The initial voltage is V0, and after some time it becomes a 0. Okay, and therefore you can consider that the source-free circuit look like a discharging curve. Okay, discharging. Now, especially for a special time, tau. Now, this tau, when you substitute into the function, V tau equal to V log e to the power minus tau over tau, and it is equal to V log e minus 1. Okay, and it gives you around 0.368 V log. Okay, or it is equal to V log over E. Okay. Now, this is what we call the time constant, tau. Tau means that it is the time you can reduce the initial voltage to 1 over E of the initial voltage. Okay? On next page, we tell you. Now, the speed at which the voltage decay can be categorized, how long it takes the voltage drop to 1 over E of the initial voltage. It is so-called a time constant, tau. Okay? And in the RC circuit, tau equal to RC. Therefore, sometimes our voltage function can be expressed into Vt equal to V log times e to the power minus t over tau. OK？ 嗱，如果你考慮呢個 discharging 嗰個狀態係你個電芯咧，你一定係想嗰個 RC 咧就越大就越好嘅，係嘛？越大越好嘅時間咧，你放電咧咪喺度咁慢慢放咯，咁你嚿電咪襟用啲咯，係嘛 ？OK。Now here we have more about discussion on the time constant. Now we say that at 5 time constant, the voltage of the capacitor will less than 1%, and we can consider that the capacitor is fully discharged or charging at that time. It depends on whether you're charging the capacitor or discharging the capacitor. Okay? Therefore, if the circuit have a very small time constant, okay, then you have a fast response, fast discharging response. Therefore, as I told you, if you have you want to have a battery to have a longer life, you should have a large time constant. Okay? You can see. If the time constant is larger, your curve will become more fat in order to sustain your voltage. Okay? I think I better stop it here and we can continue 2 weeks later, because next week we have a holiday, right?